Here's a sample. Let's say I have a boundary condition with prescribed value of phi at the boundary, like you've been doing in your homework problem. Okay? So again, always we start with the basic finite volume equation. So that's the equation after we've gotten by integrating the governing equation once. Okay? So this is our finite volume equation. What we do now is we split it up into two parts. So we are going phase from 2 to 3 instead of from 1 to 3. Okay? So this is my phase number 1. I've separated it out into a boundary phase contribution. Okay? Because I want to do a special treatment for that phase. All right? So for interior phases, the expressions that we had for the normal gradients derived earlier still hold. Exactly the same. Nothing changed. For boundary phases, we need special treatment. So how do we do that? Well, so here is our term. We want to approximate this guy. Okay. So again, we start with this decomposition in 2D, normal and tangent. Okay. And then we perform this dot product with the L vector, except that now the L vector is pointing from the cell center to the phase center, not the cell center to another cell center, as we had for interior phases. Okay. So it's pointing from O to B. So we do that dot product. As before, left-hand side, this guy becomes that phi B minus phi naught. Okay. And delta B is NB dot L. Same as before, so it's really the normal distance from the wall. Okay. So my governing equation, or the gradient, the normal gradient, this guy here, becomes that. This is again your tangential flux term at the boundaries now. Okay. Now notice that this approximation is only first order in space, and this is one of the difficulties with unstructured formulations. It's very difficult to extend things to higher orders. I mean, it can be done, people have done it, but it's pretty tedious. Okay, so normally what they do is once they get to the boundaries, everything defaults back to first order formulation like that. Okay, so this is kind of like if you have a Cartesian mesh. Okay, remember when we did boundary conditions in a Cartesian mesh, we did a Taylor series expansion of this about that and then this about that to derive a second order expression. Okay, now what we are doing, we are simply saying derivative at the boundary is nothing but this value minus this value divided by that distance. All right, because we can't do those 2-point nice Taylor series expansions anymore. So that's what is defaulted to. So the boundary always sort of contaminates the solution a little bit. But of course, even for interior cells, you're not guaranteed second order in this case. Okay. So that's one thing to remember for an unstructured formulation, especially if you're using triangles. It's kind of difficult to do. Okay, so now we get to this term, which is your tangential flux. What do we do with that? Okay, so this guy here is again just like before, phi B minus phi A divided by the length of that tangent, which is nothing but the area of the boundary face. Okay, and so my JT becomes that. Okay, this guy is nothing but your area of the boundary face. Okay. And so one very interesting thing happens, and that is if you have a uniform value over the whole boundary patch. So suppose I'm solving a heat conduction problem, and I say temperature here is 200 degrees. Okay, so that means all these vertices have a value of 200. Okay, now if that happens, notice what happens here. Phi B is equal to phi A. Okay, those are vertex values. So that tangential term drops out because there is no tangential gradient along the wall. Okay, the values are the same. So when you have Dirichlet boundary conditions with uniform values on a given patch, then that term drops out. Okay, and you're back to just this part. But that may not always happen. For example, the homework problem that you've been solving, you had phi distributions on the face. Okay? So in that case, you have to be cautious that this term will not be 0. But this is a special case where nice things happen. Okay? And so your final expression becomes this. So this is for what we just derived for the boundary condition. This is what we have for interior faces going from 2 to 3. So this is an extra term due to the boundary condition that we have. Okay. So now notice, if I think about now my, so that's the final expression. These guys we are going to transpose to the right hand side, explicit treatment. Okay. And then these guys are boundary values at the vertex, which are known. Okay, because it's a Dirichlet boundary condition. So one thing I want to just talk about here is, if you now look at this, okay, so this is your A naught, the diagonal of your matrix. So diagonal of your matrix is the fact that this came from the boundary doesn't really matter. I could have actually done a summation from 1 to 3 gamma f AF over delta f, because this is the same as that, except it's for phase 1. Okay, so your A naught will be simply summation of gamma f AF over delta f. That's it. Okay. As far as the neighbors are concerned, I just have 2 neighbors now, the 2 interior faces. The third neighbor has disappeared from the equation, which means that a neighbor of the boundary face has been essentially set to 0. Okay, which is what I was talking about earlier on when I said that the custom is to set the a neighbor to 0 at the boundary and then move on and add these guys as source terms. Okay, and you can see they have become source terms now. They're on the right hand side of the equation. Okay. Neumann boundary conditions are very straightforward. Again, we talked about this, that in finite volume formulations, Neumann boundary conditions are easy to implement. Why? Because this guy is given, so all you do is you plug it in here. Okay, and that's it. And then rearrange your equation, you're done. Okay, whatever expressions you had for the interior faces, you still use there and code it up, and that's it. And then your source term just gets modified because of that boundary flux. All right. So that's your Neumann boundary condition. Robin boundary condition is slightly more complicated because you have a combination of the two. So I'm just going to kind of go through this quickly. So I've broken it up again into 2 parts first. Then I have my expressions that I derived earlier for Dirichlet boundaries. Same thing. Robin boundary condition says from this expression here, I can derive this. Write phi b in terms of the normal gradient. So I can plug it into this expression right here. Or sorry, not there, here. Okay. So that's what I get. So I think what I have done here is, yeah, I've plugged this expression in here, and that's how I get this term. And then you rearrange, so you get an expression for your gradient. And once you have that, then you can plug it back into your original finite volume equation, which gives you something that looks like that. Okay. And of course, you can plug in your expressions for the interior faces and then rearrange everything. So you see there's a phi naught which shows up, which means there will be a contribution to the diagonal. And then, of course, there are these vertex values which show up, which are not known. You have to treat them explicitly. Okay. So here's the example problem we are going to solve. The very simplest equation I've chosen, just the Laplace equation. So gamma is actually 1 in this case. Okay. So it's disappeared. So you will find that in my code there is nothing which does cell-to-face interpolation of gamma and those kinds of things. Okay. Just kept it simple. So we are looking at that. Here are the boundary conditions. Again, very simple. Bottom wall has phi equal to 1. Everything else has phi equal to 0. Okay. It's a rhombus, 60 degrees. What I've done here is I have created a simple mesh generator which basically generates these quadrilateral cells that you see there. Okay, it's kind of like your Cartesian mesh generator. You use your I and j indices, and then you have these squares. Now you have tiny little rhombuses. Okay, and then I have numbered them arbitrarily. The way I've numbered them in the code are as follows. So I've gone again 1, 2, 3, 4, 5. Let's say if we take this example, so then 6 through 10, and then here you will end up with 25. Okay. Now the computations I did actually for 40 by 40 mesh, so 1600 cells, but this is the numbering pattern for the cells. The faces are numbered this way. It starts with here 1, 2, 3, 4, 5. Okay. Then it moves over to the next set of horizontal faces, 6, 7, 8, 9, and so on, and keeps going until here. So I think this will be 10, 15, 20, 25, 30. So this one will be 30. And then what it does is it comes down and starts numbering this one, the vertical faces, 31, 32, and so on. So you see now there is no really any kind of ordering. Cell 1 is surrounded by faces 1, 31, 32, and 6. Okay, and so on. So I have to know the connectivity or generate that information explicitly. All right. The vertices are numbered also the same way. So what I've done is I've started from cell 1 and numbered these 1, 2, 3, 4, and then I've gone 5, 6, 7, 8, 9, 10, and so on, and then kept moving up. Okay. It's just something I've created. It could be done any number of ways. It doesn't really matter in the end what numbering you do. All right, but that's just to give you an idea. Any questions on that? So this is what we are trying to solve, okay, in that little code that I've posted. The rhombus is of unit length, so 1 by 1. Okay, so this is 1, and then this here is 1. So the height is actually sine of 60 degrees, 0.866, and the quadrilaterals are of uniform size. Okay, so let me quit here and show you a little bit of this. Okay, so when you look at the code, all this top stuff you can skip. So what happens is there is a main program. The main program simply calls two routines, grid and solve. Okay, ideally you should have grid and solve and post process and all that, but I've just made it very simple. This grid routine or function essentially computes the grid and all the connectivity, and that's, as I said, 80% of the code. The rest is this guy here, which actually solves the equations. All right. Now I have a little description here of all the variables that I am using. So you can see here, these are some things that you're familiar with. LCF is link from cell to face. LCV is link from cell to vertex. So these are your cell to face connectivity, cell to vertex connectivity, and so on. So link from face to vertex, link from face to cell, area, volume. This is the interpolation function from cell to face. This one here is the interpolation function from cell to vertex, and then you have coordinates x and y of cell centers, of vertices, of faces, surface normal at faces, surface tangents at faces, boundary face to face mapping, and then the reverse face to boundary face. And then we have these two flags which states whether a face is a boundary face or not. Okay, so it's 0 for interior faces, 1 for if it's a boundary face, same for the nodes, 0 or 1. Okay, 0 if it's a interior node, 1 if it's a boundary node. And then this SN sign, remember we talked about it, that the surface normal is stored a certain way, but from every cell's perspective you have to flip it such that all of them are pointing outwards before you apply all the formulas, because that's what your Gauss divergence theorem wants. So that SN sign really stores the sign of the surface normal locally from the perspective of each individual cell. Okay, so that's pretty much all the stuff that we've talked about. Okay, a description of that. So I'll just go over this briefly. So first, I've assumed that the dx and dy or I shouldn't call it dy, but d psi 1 and d psi 2, they're equal. Okay, so this is your delta, basically. Right here. Oops. Why does it keep going away? I don't know what's going on. That guy. Okay. So let me get this out of the way. Then what I'm doing here is I'm tallying the total number of cells. Okay, now I could have just said it's n times n, but what I'm doing here, this is how one needs to really do this, is I'm tallying the total number of cells, tallying the total number of vertices. Why? So that I can store them, and then I use those numbers to allocate memory. Okay, so right here you see now I'm allocating memory for the cell centers and the vertex coordinates. Okay. This is calculation of all the cell centers. Okay. Then here we have calculation of all the vertices. This is just geometric calculation. As you can see, I'm using the angle of the rhombus to calculate them. And then here we start getting into grid connectivity. Okay. So here as you can see, I'm automatically also numbering the cells right there. Okay. And right there. So it's simply incrementing the number of each cell as I'm going through each cell, which means that really there is no pattern. It's just adding 1 to every time I count a new cell. Okay. And then what it's doing is it is linking the cells to the faces, creating numbers for the faces and linking them. Okay. Then you get to connecting all the vertices. Okay. And then we are also doing face to vertex connectivity. Okay, so this is all geometric stuff, and you have to come up with now. Generally, what would happen is all this information would basically come out of the mesh generator, and you would have that kind of just stored. Okay, so you would take that information and just store it instead of generating it yourself. And then I've calculated all the. So once I have the vertex values, which you saw already that I generated, I'm calculating the face centers, which is basically half of the two vertex values in this case. Okay, it's a simple line segment, so it's just the average. So that's your face centers, and then finally I'm also doing the indexing of the boundaries. So I think the boundaries are numbered in counterclockwise order, going from 1 at the bottom and then going all the way around. Okay, and for each one of them I have a new number, and those new numbers are then connected to, so this IFCB that you see here, this is the boundary index, and that boundary index is then connected to the global index. Okay, so the both of these guys, the boundary face to face and the face to boundary face, those indices are created, okay, or stored. All right. Okay, then let's go to, so we've done all connectivity, boundaries, face to cell connectivity, and then we get into calculation of the, or processing of the geometry. So this is where we are doing area calculation right there. So you can see this is nothing but a distance calculation right here. So I'm doing dx. So I'm looping over all faces, getting my two vertices. From that I know the coordinates of the vertices, and then I apply a distance formula. And then in the same loop, as I mentioned in the previous lecture, I'm calculating the surface normals. Okay, these surface normals and surface tangents have been calculated in such a way that n cross t gives you the k vector, okay, which is the unit vector in the z direction. Okay, so those are your surface normals and surface tangents. Now, generally, as I said, the surface normal is stored such that they're pointing from cell 1 to cell 2. So whatever connectivity I have created between my cells, if I take a face and I say this is my cell 1 and that's my cell 2, then the surface normal must point that way. Okay, if I say this is 1 and that's 2, then it must point that way. Okay, so my code relies on that. So therefore, now these surface normals and tangents that I've calculated, they have some direction which depended on which way the vertices are numbered, and they may not always follow the pattern that they're pointed from cell 1 to cell 2. Okay. Now, if you got this from a mesh generator, they would automatically be aligned so that it goes from 1 to 2. Okay. But in this case, since I just calculated them without referring to any kind of cell information, they may not be pointed the right way. So what I've done here is I have pointed them from cell 1 to cell 2, and also I've made sure that the external surface normals are all pointing outwards. So in other words, if this is my computational domain, everywhere on the outer surfaces they're pointing outwards. Okay. Now how do I do that? Here all I'm saying is what's going on here is I'm looping over all faces. I'm getting my two cells. Okay, so suppose I have a face here. I'm getting cell 1 and cell 2. Okay, and now I'm saying if the index of cell 1 is the same as index of cell 2, that can only happen if you are at a boundary cell. So if you're at a boundary cell and you're at that face, when you get the two indices, they will be the same. That's how they're stored. Okay, so I'm making use of that to identify that this is an interior face or a boundary face I'm looking at. And in that case, what I'm doing is I'm calculating n dot L. Remember that L vector? So here's my boundary. Okay, here's my L vector pointing from the cell center to the boundary face. Okay, now suppose my n is pointing this way by mistake. Then n dot L would come out negative. Okay, so what I'm saying is if it comes out negative, then flip it. All right, so I'm making the surface normal equal to negative of itself. So I had it pointing this way. I found that n dot L came out negative, so I flipped it back. Okay, and that's what I'm storing then. So for the interior faces, here's what's going on. Suppose I am at this cell, two cells let's look at. Okay, let's call this cell 2, let's call this cell 1. Okay, now I am at this cell. This is the cell I'm looking at. From this cell, I want to make sure all my surface normals are pointing outwards like that. Okay, or I at least want to know if it is pointing out or in. Okay, I must have that information. So what I'm doing is I am at this cell. From that cell, I go to that face. So I'm saying, okay, give me the index of this face. So that's what is done. Well, no, actually it's the other way around. So what it's doing is, okay, so here what it's doing is it's saying I'm at this face. Okay, and again here's my L vector. Okay, so it's saying if n dot L is positive, then it is already pointing in the right direction because the L vector is pointing from cell 1 to cell 2 always. Okay, so if it is already positive, the dot product, then it's pointing in the right direction. You don't need to do anything. If it is in the negative direction, then you flip the sign. Okay, that's what it's doing here. The other thing I was talking about, the SN sign, we'll get to that in a moment. All right. Any questions on that? So these are important steps, by the way. All right. And this is not something your mesh generator will do for you. You have to do this, the ordering of the surface normal. And if you get that wrong, what you might find is that, instead of, let's say, a solution which should have contours like this, okay, you'll suddenly find that the contours have become like that, completely lopsided, okay, with those wrong signs. So you have to be really, really meticulous about this. And then, the way, for example, when I wrote this code, I didn't try to do a 40 by 40 calculation. I did a 3 by 3 calculation. And I actually drew a picture, wrote down each of the cell numbers, each of the vertex numbers, each of the face numbers, each of the values of surface normals, to make sure that it is exactly what I think it should be. Okay? Once you have made sure that that's the case, then you can go to 40 by 40 very easily. But you got to make sure that each distance, each normal, each area, each volume you're calculating makes sense. So for example, when you print out volumes or areas, they should be what you think it should be for that rhombus. Okay? So each of my lengths are 1, so if I make 3 cells, they should be all 1/3. If they're not, then something is wrong in your calculation. Okay? Those kinds of obvious things you have to check. There's no bypassing that and saying, okay, I'll just write the code and hope it works. All right? Okay, so that's the surface normal. We talked about pointing it in the appropriate direction. Now we are calculating here the n dot L. Okay, so here is your dot product basically. So you see here, this here is nothing but n dot L. So here is your n components, nx and y, and this dx1 and dy1 are nothing but, as you can see, the distances between the two cell centers. Okay, so that's what that is doing. And then I don't know why it keeps rolling back every time I okay, so we talked about n dot L. Where is it? Here. Okay. And then this is what I was talking about earlier, making the surface normal, making it point or storing its sign from the perspective of each cell. So what it's doing here is like this. Here are your two cells. Okay, this is cell naught, let's say. Okay, so from cell naught, I'm looping over all cells, as you can see here. Okay, I visit that cell. From that cell, I go to that face. Okay, and I want to find out, is the surface normal pointing this way or is it pointing that way on that cell? Is it pointing in or out of my control volume? Okay, of control volume naught. So what I do is I go to that face, and from that face, I know already that surface normal is pointing from cell 1 to cell 2. Okay? So I get the index of cell 1. Let's say cell 1 comes out to be that, and cell 2 comes out to be that. Okay? So then I know my surface normal is pointing that way. Okay? So what I do is I ask the question, is the index of cell 1 the same as the index of the cell that I am at already? Okay? If that's the case, then that means that it's actually pointing this way. Okay, because then 1 would be here and 2 would be here. Right? Because if I make the comparison of is cell naught the same as cell 1, then 1 would be, if the answer is yes, then 1 would be here, 2 would be there, surface normal is pointing that way, and I'm in business. But if it's not that, if it doesn't match, then I know surface normal is actually pointing this way and I need to flip it. Okay? So that's doing, it's comparing, IC is node naught, okay, or cell naught. C1 is this guy, 1, okay. If they are equal, then we are saying, okay, just store the sign as 1, which means it's already pointing out. If it's not equal, then store a -1, which says that it's actually pointing inwards rather than outwards. Okay, so -1 is inwards, 1 is outwards. That's what we are storing here. Any questions on that? All right, then here we are calculating the interpolation functions. Okay, So straightforward application of formula. All we are doing here is, so this is face to cell interpolation. So here are two cells. Okay. Notice what we are doing. We are looping over all faces. Okay. So I'm at this face. From that face, I'm getting the two cell indices. This guy, 1 and 2. Okay. And then I'm calculating this dx1, dy1, which are, so if you take that as the face center, dx1 is this x minus that x, dy1 is that y minus that y, and so on. And then I get dx2, dy2. With dx1 and dx2, I'm calculating the length, so that length here. Okay. And then I'm calculating that length. And my weighting function is basically d2 over d1 plus d2. The original formula is 1 over d1 divided by 1 over d1 plus 1 over d2. It's inverse distance weighted, remember. So, but if you simplify it, this is what you get. Okay, that's what you see here. So that's your weighting function. Okay. Now it turns out in this problem, actually, since we are not having to interpolate gamma at all, this is never used actually. Okay, but it's there in the code. And then the same thing we are doing for vertex. In the case of vertex, we may have something like this. Okay, so here's a vertex. I want to calculate the weighting function out of those 5 cells, and that's what this is doing. By the time I get here, it's added up the contributions of all the 1 over d's from the different cells. Okay. Some of the things you have to remember, for example, here I've hardwired the number of cells that contribute to the vertex as 4, but in a general unstructured code, those will be variables. Okay. Same thing here. Okay, and I put a comment here saying it's assuming 4 vertices of each cell, and so on. All right, so that's your interpolation functions. Here is cell volume. This is basically the formula that, actually I'm using the area formula here because volume in 2D is nothing but area. So that's what I'm using. Okay, so this is just a cross product calculation it's doing. This first part is, this part here is the first triangle, and then this part here is the second triangle because it's a quadrilateral. All right, so that's that. Then final few things, you tag your boundary nodes right there. Whatever nodes are at the boundary, you assign a value of 1, and that's it, you're done. Now somewhere up on top I've also tagged the boundary faces. Okay, so all the quantities we need are there. So this is, as you can see, I mean, I've already gone, if you look at the slider, this is about maybe about 30% of the code already done. Okay, and then this part, in fact, here is just printing out. So this is where I make a, this is another good habit to do. See, what I'm doing here is I'm introducing a flag. Okay, I'm calling it info. That info can have different values. So for example, info can be 5. Okay, so here is how you would usually do it. Suppose info is 0. Okay, then that would mean you want to run the code without printing anything at all. It's like a production run. So you just set your info to 0. It will never even print out any of this stuff. It will just crank through the code. All right. Now suppose you want make, now this guy can be at different levels. Okay, I can have it staggered where I say if info is greater than 5, then print out all the surface normals. If info is greater than 3, then it will print out surface normals, volumes, areas. Okay. If info is greater than 0, then it will print out everything. Okay, so you can stagger it based on how much details you want. Because these printouts can be very large for a mesh, for a big mesh. All right, huge files. So you need to be a little careful. But this is how you would not have to comment and uncomment every time when you write a code and want to look at data. All right. Okay, so that's just a little pointer on printing. Okay, and then we get to the main thing, the subroutine called solve. Okay, now there are many things I've sort of hardwired here because I don't have a mechanism here of actually arbitrarily selecting a surface and specifying a boundary condition and stuff like that. So all that stuff I have to do. Normally, if you use a mesh generator and a graphical user interface or some kind of graphical tool, you will have information because boundary condition is inherently tied to geometry. So, you can't separate the two. So, those things come together from the mesh generator. But here, of course, I don't have that luxury. So, you will see that some of the things I've hardwired, okay? For example, right here, I've hardwired the bottom boundary condition. So, what have I done? I've created this array called phi b, which is the phi value at the boundaries. Okay, it's set to 0 initially because I know I have zeros on all the other boundaries. And then all I'm doing is I'm saying if the y value is less than a small value, set it equal to the bottom boundary condition, which is 1. Okay, that's where I'm hardwiring it. And normally you wouldn't do that. Okay, that's obviously bad practice. Okay, so that's the thing. Now, one word of caution, and this is something I see students often do. Often I see students do this. If phi b is equal to 0, or sorry, if y is equal to 0, then phi b is equal to 1. Okay? That's bad coding. You can never compare real numbers in a code. Okay? This will immediately give you different answers for different machines, different computing languages. Okay? Do not ever compare real numbers. Use logic that compares real number to do something in a code. You can only do that for integers. You can say if I equal to 0, then do this. If I is equal to 23, do this. Okay? You can't say if x is equal to 23, do something. Because some computers will think that logic has been satisfied. Some other computers will think, no, that logic hasn't been satisfied, depending on the precision of the numbers it stores. Okay? So what you need to do is, suppose you want to implement the logic that, okay, if x equal to 23, I want to do something. Okay? What you should do is you would say if absolute value of x minus 23 is less than some tolerance, then do whatever you want to do. Okay? That tolerance could be as small as 10 to the power minus 12, for example. Okay? So what are you saying? You're saying that if I am really close enough to 23, then do this. Okay? Sometimes that, it would be exactly 0 on some computers. On some computers, it may be 10 to the power minus 16 if you're using double precision numbers. Okay, and you don't even have to go that far. I mean, here, for example, I'm just using 10 to the power minus 3 because I know my y coordinates are in the order of point something, 0.1, 0.2, something like that. Okay, so that's something important to remember because I often see students, you compare real numbers in their codes and things then go haywire. You run it in your lab computer, something happens. You run it on your laptop, something else happens. Okay. All right. So that's a little digression. So let's get back to what we were talking about here. So that's just setting the boundary condition. I've hardwired it. Okay. Then what I do is I calculate my link coefficients. Okay. Now notice that I'm doing this outside any iteration loop because my link coefficients don't change in this case. Okay. But there could be problems where you have to do it within the iteration loop. So here is what I'm doing, okay? Okay, let's now I'll go back to my slide here. So we can just take a quick look at the equations, okay? So if you look at these equations here, what do we have? We have gamma is 1, right? So we have just area over delta showing up for your neighbors, okay? So this is your A and B. Neighboring link coefficients, and then in the diagonal you have the sum over area divided by delta over all the faces. Okay? If we go to a boundary face, what you will do is one of these guys will go away. So suppose I am at, if that becomes a boundary face, then this term will go away and it will get replaced by something else. Okay? So this code here, you will see exactly that. All right? So here's what's happening. Here's your AP. Okay. Notice I've initialized AP to 0 and I'm continuously summing over all the faces. So these are my 4 faces. Okay. I'm running a loop over all the 4 faces, that one, and AP becomes AP plus area over delta. So that's summing over all the faces if it is not a boundary face, if it's an interior face. Okay. If it's a boundary face, then I'll do something else. All right. And then here is my neighboring coefficient, which has a minus sign, area over delta. But it doesn't get cumulatively added. It's just one term. Okay. It's just the area over delta that you saw in the previous slide. All right. If it's a boundary face, then also you have that contribution, but then your neighboring coefficient becomes 0. Okay. And instead, this term gets added to the source term, because it's a known quantity. So it goes over to the right-hand side of the equation. Okay? This phi b, phi at the boundary times area divided by delta. Okay? So if you were doing a Cartesian mesh calculation, now suppose, I change the rhombus angle to make it 90 degrees. That's all you need. Now you're ready to solve. That's it. That's your code. Okay? It's as simple as that. But if you're not doing a Cartesian calculation, then you have to do other things. You have to do those skew terms. Okay? And the skew terms need to be calculated inside your Gauss-Seidel iteration, or whatever iteration. In this case, I'm using simple Gauss-Seidel. Okay? Your skew terms need to be calculated inside that. Why? Because the vertex values of phi will change every iteration. Okay? So that's why this is being done inside. So here is what I'm doing. Now, ideally, again, all this would be functions or subroutines that you would write separately. Okay, I didn't bother to do that because this was just for demonstration. So I wanted to kind of keep it transparent instead of having to jump back and forth between different procedures. Okay, so here is what it's doing. It's simply calculating the nodal values using these interpolation functions and the cell center values of phi. So I'm starting with a guess of phi. I know all my phi cell centers, so I'm using that and the interpolation functions that I already developed to calculate my nodal values for phi. Okay, and then what I'm doing here is I'm just overwriting the bottom set of vertices by the bottom boundary condition. Okay, that's again hard wiring because I don't have a mechanism to actually do boundary conditions here. Okay. So once this is done, I have all my vertex values. Once I have my vertex values, next thing I'm going to do is calculate my skew terms. Okay, so that's what this guy is doing. Now, I'll just go back again and show you the expression for the skew terms. Okay, so this is your skew term, the sum of all those guys. So notice I have phi at vertex 1 minus phi at vertex 2, and then the t dot L. Okay, this T1 and this area 1 is the same thing. They will actually cancel out. Okay, and then I'm left with this delta 1. Okay, so in the code, you will see that happening. So here is what's happening. This is exactly as in your as you saw in the slide, t dot L. Okay, t has been calculated already. This is the L vector, the two components. Okay, joining the two cell centers. I'm calculating t dot L, and then I have t dot L phi vertex 2 minus phi vertex 1, and then I have this SN sign which takes care of the fact of whether my surface normal was pointing inward or outward. Okay, I got to make it outward. So that's what this guy is doing, divided by delta, which again I've pre-processed. Okay, and I'm summing this over all the faces. So you see I'm initializing this sum to 0 and I'm just continually adding, and then this becomes my skew source of that cell. Okay, so that's my skew source. I'm done with all my sources. So this part here was for unstructured mesh really. And if you have a Cartesian mesh and you execute this, you'll find that the skew source should come out 0 if everything has been done correctly. All right. So you do that. Now this is your Gauss-Seidel here. So what are we doing here? We are looping over all cells like you do in Gauss-Seidel. Okay. Now you don't have east, west, north, south really. All you have is a summation over those 4 faces. Okay. In the summation, what am I doing? I'm trying to calculate the A neighbor, because I basically have A neighbor times phi neighbor summed from 1, or neighbor going from 1 to 4. Okay, so here's my A neighbor, which I've already set, and here is my phi neighbor. So here I'm using that SN sign to figure out what is my neighboring cell. Okay, so it's basically doing this. It's going to this face and saying, give me my index for cell 1 and cell 2. So it gives you, let's say, 1 and 2. Then it's saying, if this is 1 and that's 2, then its surface normal is pointing that way. Then the neighboring cell is 2. If this is 2 and that's 1, then the neighboring cell is 1. That's the logic it's using here. Okay, so that it can then multiply that. Okay, and then it's doing phi is equal to source plus Q source minus this guy. Why minus? Because my equation is A naught phi naught plus summation over neighbors is equal to Q naught, right hand side. So these terms get transposed over to the right hand side in Gauss-Seidel, as you know. So that's why you have a minus sum f, okay, divided by the diagonal A naught. That AP is nothing but A naught. So that's your Gauss-Seidel iteration right there. Okay, and then we're computing residuals. Same thing, same formulas, exact same thing, nothing different. Just squaring and adding the whole equation, as you can see right here. Okay, that's your L2 norm. And here's the end of the iteration loop, and checking to see if tolerance criteria has been satisfied, and then every iteration I'm printing out the residuals on screen to see where it's going. Okay, and then here's the end of my iteration loop. And after the thing has converged, I'm processing the nodal values one more time. This is not really necessary. I could have it one iteration old, but I'm doing it one more time so that I can write out all the data in finite element format, because I use TechPlot and it requires the data in finite element format. Okay, so that's all that's going on. So if you really look at this, the actual solution is pretty short. Okay, I mean, this part, as I said, is calculation of the link coefficients. This is your Gauss-Seidel, where is it? Yeah, this is your real Gauss-Seidel loop. Okay, if you did not have any skewness, if you had just Cartesian mesh, then all this stuff is not necessary, and that's it. Okay, so really a lot of work on the pre-processing end, how you take the mesh, process all the information to have them at your fingertips. Once you have them, then writing of the code is pretty straightforward. All right, any questions on that? So go over this if you can, and try to make a connection to the equations on the slide so you see which term is which and what's being done. Okay, that will give you a better idea. It's hard to understand when I'm going through this in such a rush. So anyway, let's move ahead and look at now. So here's a picture of the mesh that was generated. This is actual, this is not a schematic. This is the actual mesh that we generated, 40 by 40. Okay. And as I said, I used Gauss-Seidel for iterative solution and used a tolerance of 10 to the power minus 8. Okay, and here is the convergence. So it converges in around 2000 iterations. In fact, next class I will show you the convergence when we do coordinate transformation and solve the same problem on the same mesh using body-fitted coordinates, and you will see the convergence is just a tiny bit above 2000 in that case. Here it's a tiny bit less. Okay, so that's your convergence, and then this is your solution. So as I was saying, one of the things is making sure that all the directions of your surface normals, tangents, and so forth are consistent and in the right way, done the right way. If they're not done the right way, here is, for example, what you might get. This contour that you see, okay, this is actually the right solution, because what you see here happens is, because this is a far corner, the information of this boundary doesn't go to that corner as much as it goes to this corner, which is closer to that boundary. Okay, so the contours are kind of skewed to the left. Okay. If you do the signs the wrong way and calculate your skew terms the wrong way, you might find your solution do this. Okay, so unphysical solution essentially. It'll do what it's not supposed to. Okay. So those are kind of symptoms you will see if the skew terms are not done right. Okay. Any questions?